Okay, so I was grading your homework quizzes. Yeah, and you know, it's always easier to grade homework quizzes where everybody gets what they're doing right. It's much harder when everybody misses what they're doing. And I realized in grading your homework quizzes that many of you, especially in terms of the Graham-Schmidt shit, you were doing it the way that I went through it in class, where I was trying to find an orthonormal basis, but I was treating the higher level basis vectors in terms of these unknown functions, and then you use that the inner product had to vanish to find the unknown functions. And that's what most of my exposition in class was doing. However, I made an observation that the unknown functions ended up just being inner products. And then I showed you a formula in class, which is, you know, an orthonormal basis vector at the m+1th level, and it's based on the lower orthonormal vectors and their inner products. Many of you, when you were using the Graham-Schmidt on the quiz, was using this unknown method. So, and that led many of you to making some mistakes. Most of you got the first vector right. In fact, I think everybody got the first vector right, but most people got the third vector wrong. Okay, so that's the first mistake. The second mistake was when people depended on the other question, which was, is this matrix diagonal? And there were quite a few people who were actually doing the determinant wrong when they were trying to find the eigenvalues. So instead of taking off numerous points, this is what I'm going to propose to you. If you print out a copy or create a copy, whatever you want to do, of the homework quiz from last week, okay, and many of you might have noticed I had the solutions up, but I took them down. So if you print out a copy of the homework quiz from last week and do both questions in their entirety and hand it in this Thursday, I will grade that as opposed to grading what you turned in. And if you don't turn anything in, I'll just grade what you had turned in for your homework quiz last Thursday. So if you're confident that you'll get a good grade on that, you don't have to do this. But I just want to give you the chance to correct the minor errors that you made, but to understand that more general equation that I gave you. And I also rewrote it a little bit in the notes so it's even clearer. So by all means, even if you've already printed out the notes from that lecture where I talked about Graham-Schmidt, go back to the notes that are in there because I did put in a couple of examples. Also, I should add that after today's lecture, the question about can you diagonalize a matrix will radically change, and you're allowed to use anything we do today to answer that question. So many of you might find that one much easier with what we're doing today.
Are we still going to have a quiz on Thursday?
Yes, you're going to have a quiz on Thursday over the new homework assignment, but you also have the opportunity to do those two questions. And I promise you that quiz should not take you that long, especially if you've got the right Graham-Schmidt formula to use. Okay? So you don't have to do it. You can just take the grade you got on your work that you did, but I'm giving you all the opportunity to do that if you want. Okay? Other questions? We got a little chat room going. Let's see what's in the chat room. Can you confirm I... okay.
Maybe someone did it wrong before I spent time to redo it.
Sophia, I can't hear you. You keep, bowing in and out.
I'm even leaned all the way up close. Can you hear me now?
I can hear you now.
Cool. Can you just confirm that I did it wrong before I take the time to redo it?
Yeah, you did it wrong. Redo it.
Okay.
All right, so I'm going to get going.
Oh, I just have one more quick question.
Yeah.
So did people have a lot of problems with question 1? I guess I'm kind of asking what Sophia was asking.
Yeah, it was largely going on to the... Hold on, which one is question 1?
Diagonal.
Question 1 is the one about diagonalizing.
Oh, yeah, people had different I mean, there's a few people that got it right, and there's a few people that got the Graham-Schmidt largely right. So I don't want to say that everybody screwed up, but many of you did. Majority of you did.
Did I get question?
I'll have to go back and look at it. If you email me and ask me, I'll send you an email.
Okay.
Okay?
Thank you.
All right, so here's what we're going to do if we can get through it all. I'm going to finish up today talking about finite vector spaces, and then on this Thursday, we're going to have a very brief detour into perturbation theory, and then starting next week, we will take the infinite, or we'll take the finite, and we will blossom it into infinite. But today is going to kind of end in perhaps the most powerful statement that we might make, and I will hopefully fill in the details with lots of examples, although, and this is what sucks, because there's so many of you there, and there's so few of you here, I was actually going to give the class an activity to do, which, I don't know, I'll figure it out.
I want to do an activity.
I know, it would be nice to do an activity.
So like in person
Okay.
versus the Zoomies?
Say it again?
In person versus Zoomies?
Yeah, can we do a competition?
Yeah, we could go in person versus the Zoom people. That might be a good way to do it. All right. So I just want to very quickly start. Remember the definition of normal. So a matrix is normal if the matrix commutes with its adjoint. And then we had, so this was a definition, and then from it I ended last time with a very robust theorem that said if A is normal, then eigenvectors belonging to distinct eigenvalues.
Hey, Alex.
Hey, Madison.
For your lecture notes for today, this is the only page you have on there.
You've got to be kidding me.
I would not have interrupted class if it was not true.
Okay, hold on.
She's definitely not kidding.
All right. You think I would do that on purpose? I might do it on purpose. I'm pretty sure I do it on purpose. Okay, give me just a second and I will update it. And it is the stupidity of,
Just end class after the first page of notes.
yeah, I could end class after the first page of notes. That way we could all go into a little bit of pre-debate drinking. No, I'm not encouraging anyone to do pre-debate drinking. You should definitely wait till afterwards. Or during, which is what I'm going to do. Anyway, so boom, shakalaka. Okay, give me just a second and I will update those. Yes, replace it. Oh man, what a headache. Okay, it should be updated now. I got to get back to you guys. Nope. Here we go. Okay. Is it fixed?
Yes.
Okay, good. Sorry about that. Okay. Yeah. All right, so we ended with the statement that if A is a normal matrix, then the eigenvectors belonging to distinct eigenvalues are orthogonal, okay? Now that seems rather potent, okay? But we're going to end today with something way more potent. But we're going to start with this guy, and we'll start with a proof just to get our proof feet underneath us. So, if A is normal, then we know that AX, so the magnitude of A acting on a vector X in the inner product space squared is equal to AX, but as usual, we can move this A over by taking its adjoint. But since it's a normal operator, we can commute the A dagger in the A. And then we can have this, which implies this. Isn't that awesome? Yeah, it doesn't seem to have any relevance to what we're trying to prove. But we'll use it in just a second. Let us continue. If A is normal, and I hope you are all sensitive enough to realize that when I use the word normal, I don't mean plain and boring. I mean what the hell I wrote up here, okay? If A is normal, then so is A minus lambda, since, and we can do the following. A minus lambda dagger, A minus lambda equals A dagger A minus lambda star A minus lambda A dagger plus lambda star lambda, where what we have in mind here is that this is a matrix, this is some scalar, and it's secretly multiplying the identity to make the matrices that we're subtracting. Okay? The identity does nothing. You can transpose it, you can complex conjugate it, it just remains Mr. Identity. But of course, if you're doing the permission conjugate of this, or the adjoint of the scalar, then you're just complex conjugating it. So, if A is normal, I can flip these two. But now, I can factorize this bad boy into A minus lambda dagger. Okay? All I'm doing is showing that this operator is normal. That is, if I take its dagger times the original thing, that's the same as the original thing times the dagger of it. Okay? And now what we want to do is we want to plug this into here. So what we're going to have is AX minus lambda x squared is equal to A dagger x minus lambda star x squared. Okay, I'm really just taking A minus lambda and plugging it in here and here. Okay. And this, of course, implies that if AX is equal to lambda x, that is, if lambda is an eigenvalue of the operator A, then A dagger x equals lambda star x. Okay? If this is 0, this is 0. All right? I'm not saying that this is equal to this. I'm just saying if one is 0, the other one's 0. Okay? Now, if A x1 is lambda x1, so now I've got a particular eigenvalue lambda 1 and the associated eigenvector x1, and then we'll consider a second eigenvalue with its associated eigenvector x2. All right? Then we have x1a x2 is lambda 2 x1 x2 and x1a hold on a second. Yeah. Is also equal to a dagger x1 x2, which is equal to lambda 1 star x1 x2, which is equal to lambda 1 x1 x2. Okay? So remember, a dagger on x gives me lambda star x. Yeah, there it is. So that's all I'm doing here, but this is lambda star on the first term of the inner product, and when you pull a constant out from the first term of the inner product, you have to complex conjugate it, so that's why it's only lambda here. Okay? We good? Lucas, are we good?
We're good.
Awesome, thank you. Whew. Anyway. Yeah, I know. Okay, so these two things are identical. So that means that these two things are identical, which means if I subtract them, I'll have lambda 2 minus lambda 1 times the inner product of x1 and x2. And that has to equal what? Anna. What's that equal to? Anna?
Here we go.
Yes.
The lambda 1 minus lambda 2 thing.
Yes. What's this equal
So
to? Lambda
that's
2
gonna be
minus
0
lambda 1.
if x1 and x2 are orthogonal, if lambda 1 and lambda 2 are not equal.
Okay, yeah, so well, I was asking you an easier question. I asked you what this was equal to, and the answer is 0. But you are so sophisticated, you went on ahead and drew conclusions from this, which is,
Hard to see.
yeah, I know, if lambda 1 and lambda 2 are different, distinct eigenvalues, then this is not 0. That means this must be 0, which means these are orthogonal. Okay? We all on board? So this bad boy has been proven, but we're going to get way better than that. Now, before I continue, I'm going to drop a little example, or maybe a big example. Give you some sense of how this plays out.
So is the big reason why this works for normal matrices and not, well, operators I should say, and not necessarily for non-normal ones, is because of the fact that you get the complex conjugate of the eigenvalue?
Yep. That's exactly it. Okay, now I wanna drop an example in your lap. So I'm going to go through this pretty quickly, and I won't do it in detail. But consider the following matrix: 3, 0, 0, 0, 0, 0, 0, 1, 2, 2, 2, 2, 1, 2, 2, 1. Okay? Now, first of all, notice A dagger equals A. This is composed of real numbers. So the adjoint of it is just a transpose. This is symmetric. Okay? So this is self-adjoint. But being self-adjoint means that it is, of course, normal. So the eigenvalues of this, and I will not do this in detail, are, and I'm going to call this lambda 1, lambda 2, lambda 3, lambda 4, just so that we can match up what we're talking about. There are 3, 5, 1, and 1. Okay? The eigenvectors now, I want you to understand that A is normal. Therefore, the theorem I just presented and proved to you should apply to this situation. Okay? We have two distinct eigenvalues, and when we have two degenerate eigenvalues. One of the things that we should find is that the eigenvectors associated with these two eigenvalues should be orthogonal to each other, and they should be orthogonal to these. However, these eigenvectors, whilst they are orthogonal to these do not have to be orthogonal to each other. Okay? And I'm just going to demonstrate that through this example. So if I find the eigenvector associated with the eigenvalue 3, then that comes out to be A, 0, 0, 0, where A is anything. And we, of course, could normalize this, in which case my eigenvector looks like that. If we then find the eigenvector associated with the eigenvalue 5, and I'm assuming you're comfortable with the eigenvalue procedure. If you're not, this is something you can work out in more detail. This comes out to be 0, B, 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 where B is anything. And the normalized version of this would be 1 over root 3 times 0, 1, 1, 1. Okay? And then x3, which is the eigenvector associated with the eigenvalue 1, is going to be 0, A, B, C, where A plus B plus C equals 0. And the eigenvalue x4 is going to be C, D, E, F, where D plus E plus F equals 0. Okay? Now again, all of this would just come from you doing an analysis of the eigenvalues and the eigenvectors. I can't really give you normalized forms of these because there's lots of things to choose. But let's check the orthogonality that was predicted by that theorem. So first of all, x1 hat, x2 hat equals, and I'm going to pick a card. Boyana, what's that equal to?
0.
Yes, ma'am, it is. Okay, miraculously, this is equal to 0. Well, Yana, I'm going to keep you on board for a minute. What is x1 interproducted with x3, with this guy?
Also 0?
It's also 0, okay? Notice, that makes use of the fact that, well, this is A, and then it's all zeros. Well, the A goes with that, the zeros go with that, so that's 0. But what about x2, x3? Boyana, one more time.
Also 0.
Oh, yes it is. Because all three of the elements of here have to be the same. So you're taking A plus B plus C, you're multiplying it by the factor of B here, but A plus B plus C equals 0, okay? So clearly, we have all of the requisite orthogonality I promised. I said that these two eigenvectors would be orthogonal, and 3 would be orthogonal to this, 3 would be orthogonal to that, 2 would be orthogonal to 3, and 2 would be orthogonal to 4. But what about x4, x4? Sam Riddle! Answer the question. I'm not going to hold your card up.
No, it depends what you pick for D, E, and F.
Sorry, say it one more time.
It'll depend what you pick for A, B, and C, and D, E, and F.
Exactamundo. Exactamundo. Let's look at a couple of examples. We could take x3 to be 0, 1, minus 1, 0, 1 plus minus 1, 0, and take x4 to be 0, 1, 0, minus 1. In this case, is x3 orthogonal to x4? Sam?
No, they are not.
No, they're not. The unit product gives you 1. However, what if I take x3 to be 0, 1, minus 1, 0, and x4 to be 0, 1 half, 1 half, minus 1?
Then they are.
Then they are. Okay? So, I'm not saying that these can't be orthogonal to these. I'm just saying there's nothing that's forcing them to uniquely be of any form and be orthogonal to these. Okay? The only thing you have to be careful when you're finding the eigenvectors, especially when you're looking at the eigenvectors of a degenerate eigenvalue that appears more than once, its algebraic multiplicity is more than 1, you want to make sure they're linearly independent. Okay? These are linearly independent, so they're both good in terms of serving as a basis, but if you want an orthonormal basis, then you need to be more careful in how you choose them. Okay, so we all on board? Any questions?
We're good.
You know what's funny? You guys aren't here, but all of them are here, so they're all going to get to touch the zebras on my shirt because they're felted. Oh, you guys will love it. It feels like zebra. And you guys are just going to have to soak it in. Sucks to be you. Sorry. At any rate, okay. Are there any questions? We're going to have the best time here without all you guys. Any questions? Okay, all right.
Alex, I just have one question real quick. So,
Yeah.
When you said that last time you said if it's normal and if the eigenvalues are distinct, then it forms a basis that spans the space.
If all of the eigenvalues are distinct,
Yeah.
then the associated eigenvectors are orthogonal. So if you have a set of distinct eigenvalues, associated with each of them is an orthogonal basis vector. If you have a set of orthogonal or a set of distinct eigenvalues that span n, if you have n distinct eigenvalues for an n by n matrix, then you have n orthogonal vectors and that spans the space.
Yeah. So this one doesn't necessarily depends on what our A through F are.
Right.
Okay.
Yeah, like it could have been that we might have, not in this particular case, but we might have found that even though this appears twice, there's only one eigenvector associated with it. If you have a distinct eigenvalue, like 3 is distinct, it's different than everything else on the list, you know there's at least one eigenvector attached to it. When something is repeated, you know there's at least one eigenvector. There could be up to 2 in this case, but there's not guaranteed to be 2 until you find them. Okay? But if all of the eigenvalues are distinct, then you're definitely going to get an orthogonal set which spans the space. All right. Okay, so now I want to get to the question, when can we do you have a question? No, you're just playing with your, okay, you're playing with your pen. All right, so now my question is going to focus on this idea of when can we diagonalize a linear operator, a linear transformation? And I want you to remember, and this actually addresses your question, if you get n eigenvectors for an n by n matrix. So if you really do get n of them, all right, then they're orthogonal, and the diagonal form of the operator is P inverse times the operator times P, where P is the matrix which is built out of eigenvectors. Okay, this is a matrix where each of these is an eigenvector within components, so each column is the components of the eigenvector. Okay, so this is the first eigenvector, it has n components, and those fill out the elements of the column. This is the second eigenvector and its components. So this is an n by n matrix. Okay, I'm just using the shorthand notation. Yes?
So this is for any matrix that, any square matrix that has the same number of eigenvectors
Yes.
as its.
Yes. Okay? All right. Okay. Now, here's an interesting observation. This is a matrix P which does this miracle diagonalization. What kind of matrix is P? Is it a symmetric matrix? Is it a unitary matrix? Is it orthogonal? Is it Hermitian? What do you think?
Might it depend on the order of your eigenvectors?
Depends on the order of the eigenvectors?
Just kind of throwing that out there.
Yeah.
So I think if our matrix is Hermitian, then P is probably unitary. That's all I got.
Okay. Well, I'm going to answer the question, and in answering the question, and I think this is hilarious to read the book, I'm going to give you something incredibly powerful. Okay? And we're going to spend some time proving it because it's so damn good. So here we go. A matrix A can be diagonalized by a unitary transformation if, actually let me put in the P, if A is normal. Forget about counting eigenvalues and counting eigenvectors. If A is normal, you're guaranteed it's going to be diagonalizable, which means that its eigenvectors are going to form an orthonormal basis for the vector space. That's huge. All you've got to do is have A dagger commute with A, and you are guaranteed that you will be able to diagonalize the operator. If you diagonalize the operator, then every eigenvector associated with the eigenvalues which run down the diagonal of the matrix, every eigenvector can be, they're orthogonal, okay? So this is what we're going to spend some time proving, and it's worthwhile to invest that time because this is incredibly powerful. But just remember, if you get a matrix and it's diagonal, the eigenvectors are damn easy to find, right? I mean, you can find various things, but you know you're going to have MAB times some vector is equal to A times that vector because these are the eigenvalues. Okay, well, you know, what does this work out to be? It works out to be this matrix times, it works out to be AD equals AD, BE equals AE, CF equals AF. Oh, it's just telling you E needs to be 0, F needs to be 0, and then A and D can be whatever, or D can be whatever you want it to be. So this eigenvalue is associated with this eigenvector, and then similarly for the others. So once you've got a diagonal matrix, it's super obvious that you've got an orthonormal set of eigenvectors. Okay? So let's prove this bad boy, and it's going to take some doing. And what I think is truly hilarious is the way the book presents it. They present these lesser theorems that eventually grow into this more abstract theorem here. We're going to start with this, and we're going to prove it, and along the way we'll prove some other theorems, which are just byproducts of this. So, here we go. We have a proof within a proof within a proof. Any matrix, I don't care what kind of matrix you're dealing with, any matrix can be expressed as A equals 1/2 A plus A dagger plus I 1/2I A minus A dagger. This, I hope, is obvious. Okay? I mean, at the end of the day, the i's canceled, so this is 1/2 A plus 1/2 A, which is A. 1/2 A dagger minus 1/2 A dagger, which is 0. So yeah, this is A. Madison is going to tell me what kind of operator this is. What if I dagger it? What if I stab it with a dagger? What do I get?
Is it Hermitian?
Yes! Yes, this is Hermitian. If I stab it with a dagger, the dagger goes here, this double dagger's out. The A dagger plus A is the same as A plus A dagger. This son of a bitch is Hermitian. But, Madison, what about this?
You didn't need to call it names.
Huh?
You didn't need to call it names.
Okay, what about this?
It's also Hermitian.
It is also Hermitian.
At the end.
Okay? So we've basically decomposed an arbitrary matrix A into a linear combination of two Hermitian matrices. Does this mean that A is Hermitian? Anybody?
No.
No, because there's an I there. And of course, not every matrix is Hermitian. I mean, that would be ridiculous if I concluded every matrix is Hermitian. That's wrong. But every matrix can be expressed as this linear combination of Hermitian matrices. However, the entire matrix might or might not be Hermitian. Okay? All right. Now, I am going to identify this as matrix B plus I times matrix C, where both B and C are Hermitian. And now what we can say is the following. If B and C are simultaneously diagonalizable, by the same unitary transformation, then obviously so is A. What I mean, of course, is that P inverse AP is just P inverse BP plus I P inverse CP. If these are both going to turn out to be diagonal, well, what do you get when you add a diagonal matrix to another diagonal matrix? You get a... Whoa, man, that's like harmony. It's wonderful. Yes?
Do we have to restrict this to square matrices?
We have to restrict this to square matrices. Don't even try and take me to non-square lands, okay? All right. Okay, so everybody follow? Now, I haven't proved anything yet. I'm just showing you that if B and C can be diagonalized at the same time by the same transformation, and if that transformation is unitary, because that's what's claimed here, then obviously that implies that A is diagonalizable by the same unitary transformation. Okay? So, we have two things to show to get the ingredients to this to work out. So the first thing we have to show is that Hermitian matrices are diagonalizable by a unitary transformation. Okay? So if B and C are in fact diagonalizable by a unitary transformation, and then we have to argue when two Hermitian matrices are simultaneously diagonalizable. Okay? Now I want to remind you, even though the discussion has descended to talking about Hermitian matrices, the result applies to an arbitrary matrix, and it turns out it's going to be restricted to normal matrices. But normal includes more than Hermitian. It includes anti-Hermitian. It includes isometric. That's unitary and orthogonal. Okay? So we're going to prove this result holds for all of them, but it goes by way of breaking an arbitrary matrix down into these two Hermitian parts. Okay? So I'm just trying to get you to realize the result I'm going to prove is not just applying to Hermitian matrices. It's going to apply to any normal matrix. Okay, here we go. This is going to hurt a little bit, so fasten your seatbelts. Yeah. Oh boy. Okay, shoot. All right, I'll just erase this, and I know it's going to suck later on. Okay, here we go. For A, we have the following theorem. Any Hermitian matrix A may be diagonalized via a unitary transformation. So this is what we're going to prove to address A. And I guess I should just remind you all, we're transforming matrices, so this is actually a similarity transformation. Okay. Okay. Now, if we're going to try and argue about whether the Hermitian matrix A is diagonalizable or not, first and foremost, if we took A and we found that it had a set of distinct eigenvalues, then Ross will be happy to tell me whether we can go ahead and conclude that A is diagonalizable, yes or no?
No, and it's because it's possible to have degenerate eigenvectors where more than one eigenvector can correspond to the same eigenvalue.
No, I said a set of distinct eigenvalues.
Oh, distinct eigenvalues. Okay, yes. In that case, then there would be n distinct eigenvectors, and then it would be diagonalizable. So,
Yes, exactly. Okay? So what we should be interested in addressing is the degenerate case. The case where an eigenvalue is possibly repeated. Because if all of your eigenvalues are distinct, every eigenvalue gets one eigenvector. If all of, and you always get, okay, I should say, if you have an n by n matrix, then you're always going to get n eigenvalues. Some of them might take the same value. Okay, that's the algebraic multiplicity. However, if they're all distinct, then you have n distinct eigenvalues. Each of them has an eigenvector that's orthogonal to the rest, and that's the argument that it forms an orthonormal set. Okay? So what we're interested in is the possible case where an eigenvalue has an algebraic multiplicity of more than one. Okay? So, this is what we're going to do. We're going to start with the smallest matrix that could possibly have a degenerate eigenvalue, and that is
2 by 2.
a 2 by 2. So let's consider a 2 by 2 for a moment. Okay, if I take a 2 by 2 matrix and I want it to be Hermitian, then its elements can be A, B, B star, C. Okay, where these are possibly complex numbers. All right, and then going very quickly through the analysis to find the eigenvalues, A minus lambda, C minus lambda, B, B star. And this ends up giving me A minus lambda, C minus lambda, minus B squared equals 0. If I solve this for lambda, I get A plus C plus minus square root of A minus C squared plus 4 times B squared all over 2. Okay? I mean, I did some algebra there. It's on the sheet, but I'm not going to write all the steps down. But this is what I end up with. I mean, that's quadratic in lambda, so you use a quadratic equation. Now, if I want the values of lambda to be degenerate, what needs to be 0?
The whole square root.
Exactly, the term under the root, because this thing being non-zero is where we get two distinct eigenvalues. But if we want the two eigenvalue solutions to be the same, then we want this root to vanish, and so the result is going to be A plus C over 2, okay? But what does that mean? A minus C squared plus 4B squared equals 0. Oh, what does this imply about B?
It's complex.
Yeah.
What does this imply about B?
And it's 0?
That it's 0. This is a squared term plus a squared term. So this is going to be 0. This is going to be 0. So A equals C and B equals 0.
It's just a scalar of the identity?
Yes. Okay? So, well, hell, that tells me that oh, shoot. That's the only allowed form for the matrix A. The only allowed 2 by 2 Hermitian matrix with the same eigenvalues is already diagonal. It's pretty sweet, isn't it? Now, I have a question, and Zan's going to throw an answer at me. Zan, now this is tricky, so I want you to think carefully about it. What kind of transformation will diagonalize this?
Linear one? A unitary one?
So I want to get a diagonal form from applying P inverse to A to P, where A is this. What does P need to be?
Just the identity?
Just the identity, exactly. Okay? So P in this case is the identity. All right? Now, Zan, I'm going to do a follow-up question because that was so easy. Are you ready?
Boy. Yeah.
Is the identity Hermitian? Or sorry, is the identity unitary?
I would guess so.
I dagger I equals I.
Okay.
Yeah.
I'm a little stuck on why a few lines that we require both terms to be 0, because if A and C can both be complex, then that square could be negative.
Oh, hold on.
Aren't they, don't they have to be real because it's Hermitian?
Yeah.
Yeah, it's Hermitian, so A and C have to be real. Okay? B does not have to be real, but it's its magnitude. Thank you for the answer. Okay? So notice, for 2 by 2 matrices, we just proved A, or we proved this theorem. All we have to do is now do 3. 3 by 3s. And then check 4 by 4s. And then 5 by 5s, 6 by 6s, 7 by 7s, 8 by 8s, 9 by 9, 10 by 10, 11 by 11. Okay, what are we going to do, folks?
Proof by induction.
We're going to do it. Well, you've got the notes, Ross. we're going to proceed by induction. So we're going to show that if an n-1 times n-1 Hermitian matrix is diagonalizable by a unitary transformation, then the n by n must also be. And then we just put for our n-1 times n-1 a 2 by 2 because we just proved that it's diagonalizable by unitary transformation, and then we can go arbitrarily high. Okay? So here we go. And this is where it's going to get hairy. Suppose A is n by n. And assume that any n minus 1 Hermitian matrix is unitarily diagonalizable. And I just like words with lots of letters because that gives me more room to screw up my spelling, which I do rather often nowadays. At any rate, okay, this is just our assumption, okay? Now, here we go. Let lambda 1 be any eigenvalue of A. It doesn't matter which one. With a normalized set, or with a normalized eigenvector, x1, and x1 is going to have the components x1, 1, x2, 1, x3, 1, up to xn1, okay? And now what we're going to do is we're going to form a matrix V, and V is going to be composed of this eigenvector in the first column, and then we're going to take a set of orthogonal eigenvectors to fill out this column that are all orthogonal to this guy as well, okay? And we're going to call this thing xi1, xi2, xin. And we have that the kth vector interproductive with the jth vector is delta kj. Okay? Now, the first thing to note is that V dagger V equals the identity. How can you see that? Is it obvious?
Yeah, I mean, all the vectors are with the normal. So.
Yeah, I mean, if you think about it, what does this dagger do? It transposes and then complex conjugates the vectors here. But if you think about it, that takes this vector, and then after you transpose and complex conjugates it, if you take the inner product, well, actually, the off-diagonal contributions to this come from taking this vector and making an inner product with a different vector, but they're orthogonal. Okay? You just have to write a vector, or write a matrix whose columns are orthogonal vectors, and then do this operation, and you'll very quickly realize, oh, okay, I see, it works out. It turns into the identity. Okay? I'm not going to prove that to you right now, but hopefully if you think about it hard enough, it should be obvious. So V is unitary. Okay, here we go. Then V inverse A V ij, that is, if we think of this as a transformation of A, so we do the inverse times A times V, the ijth component of this is equal to, if V is unitary, what is V inverse? Yeah, it's V dagger, V Hermitian conjugate. A V ij, and if I break this down into the summation notation, okay? Here we have a sum over k. Oh, no, hold on. Yeah, sorry, this should be km. Looking further down the page. So we have a sum over k, which is the first index here, the first index here. Notice this is V dagger, so this is the transpose. So normally, if I want to take two matrices and multiply them by each other, then I do something like this: VIK, V prime KJ, and this gives me the ijth component. Okay. So remember, if you want to use the summation convention, you have to have your indices next to each other. However, we're transposing this. So that's why the k is on the left instead of on the right. And then, of course, we're complex conjugating it because that's part of the adjoint thing. Okay? So this tells me that if I focus on I1, that is, I take the first component of this, j equals 1, then this becomes sum over k xki star lambda 1 xk1 what does this come out to be? Any takers? Notice. So don't worry about all of this index assignment and flippage and all that stuff. I just want you to focus on this right here for a moment. Go ahead.
Isn't it just the, well, never mind.
Well, here, I'll rewrite it slightly.
Yeah.
That's xki star xk1. Remember, the i's, the second index on the components is what is labeling a vector. So that's the vector indexed by I, so it can be any vector, complex conjugated, times, it's actually an inner product with the vector v1.
It's 0 every single time except when I is equal to 1 or k is equal.
Yeah, delta I1 will do that for you. Okay? Now, you can play a very similar game. Well, no, I'm actually going to do this. Oh, goodness, this is going to take forever. This is horrible. Okay. All right. So if we consider V inverse AV dagger, so we're basically doing the Hermitian conjugate of this, then this becomes V dagger, A dagger, V inverse dagger, which is of course just V inverse AV. Okay? Then, I should say, so V inverse AV is Hermitian. Because this is V inverse AV dagger is equal to V inverse AV. That's a Hermitian matrix. Then V inverse AV, 1i, is equal to lambda I delta 1i star, which is just lambda 1 delta 1i. Wait a minute, hold on. Oh, I forgot the complex conjugate on that lambda. Or did I? Don't I need a complex conjugate there?
It's real.
It's real, why?
It's normal.
Yeah, it's normal. It's an eigenvalue of a Hermitian matrix. Okay? The eigenvalues of Hermitian matrices are real. It's not necessarily normal because, for example, orthogonal matrices, which are normal, they can have complex eigenvalues. Okay? But it's Hermitian. Okay, therefore the eigenvalue is real. Okay, so then, and I'm just going to have to erase this to make some room. Oh, man. Taking a lot longer than expected. Okay. This means that V inverse AV comes out to the following. Now, what I've been doing is I've been evaluating the IJ. Well, actually, I've been evaluating the I1 component. That's the first column of this matrix, and now I've got the first row of this matrix, and all it's saying is that It's zeros everywhere except the 1, 1 component. And the 1, 1 component is lambda 1. And then what we can say is that the rest of the matrix is some A prime matrix, which is an n minus 1 times n minus 1. Okay, I should draw zeros here to encourage people. Those are in fact zeros. Okay? Now we can define this to be the matrix B. All right? But recall our assumption. This is an n minus 1 by n minus 1 matrix, so it is unitarily diagonalizable. That means diagonalizable by a unitary transformation. Okay? So B is unitarily diagonalizable. So B might be diagonalizable via a transformation of the form W inverse B W, where W is equal to 1, 0, dot, 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 0, dot, 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 V prime, and since V prime is unitary, so too is W. Okay? So what we have in mind here is that A prime diagonalized is V prime inverse A times V prime. So V prime is the n minus 1 by n minus 1 matrix, which diagonalizes A. Okay? So if you want to diagonalize the whole thing, you just use 1 and B prime. All right? Okay, so we've got all this nice stuff, but what about A? Is A diagonalizable? Okay, I mean, after all, this is not A, this is V inverse AB. So let's have a look. We have W inverse B W equals W inverse V inverse A V W. Okay, that's just putting in for B, V inverse AV. Oh Lord, this is VW inverse. If you have a product of matrices and you're taking the product of their inverses, then that's the reverse order product inverted. AVW. This is U inverse AU. With U being defined as VW. Okay? So all we have to do is show that U is unitary, and we're done. Okay? So to show that U is unitary, just U dagger, VW dagger is W dagger, V dagger, which is W inverse, V inverse, which is VW inverse, which is U inverse. But if U dagger is equal to U inverse, U is unitary. Okay? So what we've proven is that a Hermitian matrix A is diagonalizable via a unitary U as long as the n-1 cross n-1 matrices are diagonalizable. Okay? So now let's do what I said we should do at the beginning. Is a 2 by 2 matrix diagonalizable? Yes. Now, what about a 3 by 3? Yes, because a 2 by 2 was. What about a 4 by 4? Yes, because a 3 by 3 was, etc., etc. Okay? Oh man, this is hellacious. Actually, yeah, I think I can finish this up in just like 5 minutes. So I'm going to save the activity and actually make it your homework.
I'll just stay an extra 15 minutes. It's okay. Just do it.
Actually, we won't. Well, we can break now and just finish up on Thursday, if you'd prefer, or I can keep going. It's up to you guys. Do you guys want to vote? Who says keep going? Who says stop now? You guys good with stop now? We'll just continue this story on Thursday. I see a hands up or a thumbs up. Thumbs up. Okay, all right, we'll pause there. And remember what we have to prove when we get back. We have to figure out when you can simultaneously diagonalize two Hermitian matrices. That's the B and the C. Because you have to be able to simultaneously diagonalize them. Let's use the same transformation to diagonalize them both. Then their sums are also going to be diagonalizable. So we'll start next time with that. All right. I will see you all Thursday. Hopefully you heard what I said about the homework quiz. If you didn't, go and listen to the beginning of this lecture once it's posted so you know what you can do. Okay?
Thank you, Alex.
Thanks for answering questions, guys. I really appreciate it.